So far, we have seen how to construct a root locus. Today, we are going to see how we can design a control system by using root locus. So already we have seen that we put an amplifier. If we put an amplifier here, we can adjust the static gain of the system. Static gain of the system we can adjust. But we cannot, from third order onwards, we cannot increase this K beyond a certain value. That is called K max. If we increase beyond that K max, the system becomes unstable. That is one way of designing a system. That is only one parameter we can vary. So we cannot modify the structure of root locus. We can select one point on the root locus so that the characteristic of the system is a desirable one. Suppose our pole is not on the root locus. The desired pole is not on the root locus means you cannot modify the root locus by simply adjusting K. But if you want to modify the system, instead of putting K only, we can place in place of K tau s plus 1 upon alpha tau s plus 1 multiplied. That K also you can keep. So this is this system can be included here. Instead of simply K, we can include the system here. Here, what and all we included? Static gain, 1 0 and 1 pole. Where is the 0? 0 Z equal to minus 1 by T. Where is the pole? Compensatory pole, minus 1 by alpha tau. So if we include this way, 1 pole, 1 0 is included, means the structure of root locus itself modified, so that the new root locus will pass through the desired pole, so that we can modify the characteristics of the system. That is called compensation. That is called compensation by using subsystem. Compensation using subsystem. So that is called design of control system using root locus. Design of control system using root locus. Here, if you see that this is a first order system. First order system. Because only one pole, its root locus going to infinity, minus infinity, as K increases from 0 to infinity. That's all. This is the root locus. Suppose if I include one pole to that system, already one pole is there. I have included one more pole. Already one pole is there. I included one more pole. What happens now? Already one pole is there. I included by like this one subsystem 1 by alpha tau s plus 1. So I included a pole at minus 1 by alpha tau. I included. Here I included. Earlier, what is the root locus? This is the root locus. Now, two poles. P1 is the original pole. Now I included P2. Therefore, both are starting points. The root locus will not available after this point because 2 is right even number of poles and zeros. Therefore, this is also starting point. This is also starting point. Both are starting points. That's why there will be a breakaway point. One goes up and goes down. So if we include one pole, the first order system root locus becomes like this. So we modified the root locus simply by adding this subsystem. Still it is stable only, but here it is over-damped system. Over-damped system. Now it becomes over-damped, critically damped, under-damped system. Depends upon selection of pole. Suppose you select the pole here, Suppose you select the pole here, then system becomes underdamped. Suppose you select the pole here at this point, that is breakaway point, the system becomes critically damped. If we select a pole here, system is overdamped. So we can select the pole so that the desired characteristic can be obtained. Suppose I include one more pole. If I include one more pole, already two poles are there. Two poles are there. If I include one more pole, to its left, to its left, if you select any point, to its right, odd number of poles and zeros. That's why this is part of root locus up to minus infinity. These two are starting points. That's why the root locus will approach each other and break away and goes to infinity along an asymptote of angle 60 degree. 60 degree. This is minus 60 degree. This is 180 degree. But after some value of k, it crosses j omega axis. Therefore, the system becomes unstable after some value of k. So this is effect of adding pole to the system. Effect of addition of pole to the system. First order system, if you include one pole, it becomes like this. If you include two poles, the root locus becomes like this. Suppose I am taking a third order system. Suppose I am taking a third order system whose root locus is third order system. In that, I am including a pole very close to j omega axis. I included a zero very close to j omega axis. This is 1 0 included. This is original system. This is original system. No compensation. Here I included a zero. Because of that, the characteristic is modified like this. So what happens? We'll apply the rules and check whether we are getting this or not. 3 poles. And I added 1 0 here. So this is part of root locus. This is part of root locus. Because to its right, odd number of poles and zeros. It is not part of root locus. It is not part of root locus. But these two are part of root locus. These two are part of root locus. Both are starting points. Any point after this is not part of root locus. So it is not part of root locus. But between these two, both are starting point. That's why there will be a breakaway point and it goes up. One goes up, another one goes down. So in a third order system, if you vary k after some value of k, it becomes unstable. But if you include a zero like this, it becomes completely stable. For all values of k, the system becomes stable. The system becomes stable. Here, I selected a pole, I selected a zero far away from j omega axis. I included a zero in that subsystem. I included in a third order system a zero far away from j omega axis. Here I selected very close to j omega axis. Here far away from j omega axis. What happens? What is the difference between the first diagram and second diagram? The first diagram, it quickly goes to unstable. Here it takes long time to go to unstable. That is the difference. So if you include zero, even though it is far away from j omega axis, you can increase the k value. K max is increased. K max is increased. So for large value of k only, it becomes unstable. So this is the advantage if you include far away from j omega axis. If you select very close to j omega axis, it becomes stable. So if you include, you are including moderate. That is in between these two poles I am selecting. Here I selected a zero. I included in that system. What happens? These two are starting points. These two are starting points, and one goes upwards, another goes downwards, another goes downwards. Again, the system is completely stable. So we can modify the structure of root locus simply by adding a pole R0. That is called compensation. A subsystem is included here. This subsystem is what I told, tau s plus 1 divided by alpha tau s plus 1. If we include here, we can modify the root locus of original system. Original system is G of S. I included a compensatory system GC of S so that the characteristic polynomial, characteristic polynomial as well as the root locus of the system can be modified so that you will get desired response. This is called a series compensation. Series compensation. Because the subsystem is included in series with the original system. In series with the original system. Another compensation is called a parallel compensation. Parallel compensation. In that, the compensatory system is in parallel with the original system. In parallel with the original system, or the original, it is connected in between the original system. The original system G of S is separated into two parts, say G1 of S and G2 of S. GC of S is connected between G1 and G2 and output of G2, so that it will compensate the original system. This is called parallel compensation. Parallel compensation. In parallel compensation, we need some point to connect this compensatory system. The velocity compensatory system is an example for the parallel compensation. Here, this is series, very simple compensation or series compensation that we are going to see today. Here, I told you that the compensatory system may be tau s plus 1 upon alpha tau s plus 1. Here, what is this? 0 is 1 by tau s. Pole is, where is the pole? 1 by minus 1 by alpha tau. Minus 1 by tau and minus 1 by alpha tau. These are the poles. This is in time constant form. If you take t outside, what you will get? S plus 1 by tau. Here, if you take alpha tau outside, what you will get? 1 by alpha tau. So the pole is at 1 by tau and 1 by alpha tau. If this is minus 1 by tau, then it is called lead compensation. Lead compensation. Lead compensation. What is the condition for alpha? So 1 by alpha t must be greater than 1 by t. Am I correct or not? Modulus of 1 by alpha tau must be greater than modulus of 1 by t. T getting cancelled. Therefore, 1 by alpha is greater than 1, or alpha is less than 1. Sorry, alpha is less than 1. If alpha is less than 1, then it is called lead compensator. Here, this is 1 by tau, minus 1 by tau, this is 1 by alpha tau. This is pole, you know. So 1 by tau must be greater than, modulus of 1 by tau must be greater than modulus of 1 by alpha tau. It means what? Tau getting cancelled. Therefore, 1 must be greater than 1 by alpha, or alpha must be greater than 1. Alpha must be greater than 1. Alpha must be greater than 1. Then it is called lag compensator. This is called lag compensator. So either you can use lead compensator or lag compensator. It depends upon your desired system. The specification needs lag compensator. We have to go for this alpha must be greater than 1. If our specification requires a lead compensator, then we go for alpha must be less than 1. When it is called lead compensator, if 0 is very close to j omega axis, then it is called lead compensator. If pole is very close to j omega axis, then it is called lag compensator. What is the meaning of 0 close to j omega axis? Dominating pole. If this pole is very close to j omega axis, means in that system, this pole will dominate. This pole will dominate because the distance from the origin is omega. The distance from the origin is omega. Time constant equal to 1 by omega. This is, if it is very close to j omega axis, means very small number, say 1 by 0.1, that is equal to 10. Large time constant. 1 by omega is time constant. The time constant is large. Therefore, it is slow system. Lag system. Slow system or lag system. When it will be lead, when it is fast. So in that case, 0 is very close to 0. That's why 0 dominates. Here pole dominates. Here 0 dominates. 0 dominates. That's why it is a lead compensator. Here pole dominates. Pole dominates. Therefore, this is called lag compensator. Pole dominates. Here 0 dominates. By selecting either lead or lag compensator, we can modify the characteristics of root locus. By adding this subsystem, we can modify the characteristics of root locus. That is called design of control system. We are going to select an appropriate value of alpha so that the system will characteristics, that is a root locus, will be modified. So what is the subsystem? I told you that we are going to include a subsystem here. We are going to include a subsystem here. That subsystem is tau s plus 1 divided by alpha tau s plus 1, or this can be written as k tau s plus 1 by tau divided by alpha tau s plus 1 by alpha tau, pole zero method. So by selecting appropriate value of alpha and tau, we can include this subsystem into the original system so that we can modify the root locus. In that way, we can design the control system. So how to construct here? What is this? This is an amplifier. Amplifier. It may be, amplifier means it will be like this. Amplifier means this is an amplifier. If you increase this R feedback, if you increase that, the gain can be adjusted. V in, this is V out. So like this, if you can put a simple amplifier in place of K, you can vary the location of poles, but on the root locus only. But if you include this system, you can modify the root locus itself. You can modify the root locus itself. So for that, how to design this tau s plus 1 divided by alpha tau s plus 1. How to construct this system with the desired location of alpha and alpha tau. This is this lead or lag network. This is called a lead or lag network. Depends upon the value of alpha. Depends upon the value of alpha. This is lead or lag network that can be inserted into the system. That can be inserted into the system so that we can modify the structure of root locus. Here, what is the mathematical model of this? Here, this is V in. V in. Now, let us call this as V out dash. V out dash. This is V out. Two stage. This is simple amplifier. This is amplifier. This is lag or lead network. Depends upon the value of alpha. Here, what is the mathematical model? What is the mathematical model of this? V in. We know that the potential across inverting and non-inverting terminal is 0. V minus equal to V minus equal to V plus. Already V minus is grounded. V minus is already V minus is grounded. So V minus 0 means V plus also 0. This voltage is 0. Now we can write the mathematical model of this. V in minus 0. So I don't want to write what is the potential across this resistor. V in minus 0. That is V in divided by R1. That is the current. Current entering into the operational amplifier is V in divided by R1. So we are writing KCL. KCL for the junction V plus. We are writing KCL for the junction V plus. Write KCL for the junction V plus. What is the current entering from V in? V in divided by R1. That is incoming current, that's why plus. Then another current is through C1. What is that? Plus C1 V in divided dV in divided by dt. That is the current through C1. Plus another incoming current is here. What is the output voltage? V0 dash. Therefore, V0 dash divided by R2. And another current is through C2. Therefore, we can put C2 d V0 dash divided by dt equal to 0. Sum of all currents, 4 currents are entering at V plus, that is equal to 0. That is equal to 0. If we take Laplace transform assuming 0 initial conditions, or first let us multiply this R1, R2. What you will get? If you multiply this by R1, R2, you will get R2 V in plus R1, R2 C1 dV in by dt plus R1 V0 dash plus R1, R2 C2 dV0 dash by dt equal to 0. I multiplied on both sides R1, R2. If we take Laplace transform, what you will get? R2 V in of S plus R1, R2 C1 S V in of S plus R1 V0 of S plus R1, R2 C2 S V0 dash of S equal to 0. Therefore, we can write V0 dash divided by V0 dash of S divided by V in of S equal to what you will get? R1 plus R1 what you will get? V0 here you will get R2 plus R1 R2 C1 divided by R1 plus R1 R2 C2. For this, what is the model? V0 by V0 dash equal to R4 divided by R3. R4 because feedback is R4, input is R3. Therefore, V0 divided by V0 dash is this. Therefore, we can combine these two cascaded. That's why we can say V0 of S by V in of S equal to V0 dash by S by V in of S multiplied by V0 of S divided by V0 dash of S. These two getting cancelled. That is equal to this we have to include. This we have to include, that is R2 plus R1 R2 C1 S upon R1 plus R1 R2 C2 S multiplied by this. This is minus. Non-inverting terminal is grounded. Non-inverting terminal is grounded. That's why here you will get on minus. Here also you will get on minus. Therefore, both minus getting cancelled. Minus R4 divided by R3. System is, if you take R1, R2, C1, if you take outside R1, R2, C1, if you take outside, what you will get is S plus R1, R2, C1, if you take outside S1 by R1, C1, you will get whole divided by R1, R2, C2. If you take, what you will get is S plus 1 by R2, C2. multiplied by R4 by R3. So the location of pole for this system is what and all getting cancelled, this R1 getting cancelled, R2 getting cancelled. Therefore, K equal to R4 C1 divided by R3 C2. This is K. We can put instead of this and C1 by C2, we can put K. And the location of pole is 1 by R1 C1. The location of 0 is 1 by R1 C1. The location of pole is 1 by R2 C2. By selecting appropriate value of R1, R2, C1, C2, we can locate the poles and zeros. What is the system now? The system is V naught of S upon V in of S equal to R4 divided by R3 C1 C2 S plus 1 by R1 C1 whole divided by S plus 1 by R2 C2. By selecting appropriate value of C1 and R1, C2 and R2, we can place the pole and 0. Depends upon the value of R1, C1, R2, C2. Either it will be a lead compensator or lag compensator. Lead compensator or lag compensator. So how that we will see now. Here we can write this as K multiplied by S plus 1 by tau whole divided by S plus 1 by alpha tau. If it is a lead compensator means 0 must be close to modulus of 1 by tau must be less than modulus of 1 by alpha tau. Tau getting cancelled, therefore 1 less than 1 by alpha, or alpha is less than 1. If alpha is less than 1, lead compensator. What happens if lag compensator? In that case, 1 by alpha tau must be less than 1 by tau. In that case, tau getting cancelled, therefore 1 by alpha must be less than 1, or 1 alpha must be greater than 1. Alpha must be greater than 1 for lag compensator. So, based on the value of alpha tau, we can select R1 C1. Based on the value of K, we can select R4, R3, C1, C2. This is for K. This is for 1 by tau. This is for 1 by alpha tau. So that we can modify the root locus. Now, we will see how to compensate if you use a lead compensator to compensate. Suppose if the required specification of control system is I am specifying damping ratio, or I am specifying damped natural frequency, or desired location of closed loop poles, or overshoot, or raise time, or settling time. These are all the specification means. What are the specifications? If the specifications are damping ratio, omega D, or undamped natural frequency, omega N, or desired dominant closed loop poles, P and N, P and Z, overshoot, TP, that is MR, MP, raise time, TR, settling time, TS. If we specify all these things, based on that, we can find one location of poles. The poles are at this point, I can get this much overshoot. I can get this much raise time. I can get this much settling time. Like that, I can decide. For example, I am having a root locus, I'm having a root locus like this. This is a root locus of second order system. Root locus of second order system. But my desired location of pole is this. Then only I will get that required value of zeta. This is the required value of zeta, and this is omega n. I selected omega n and zeta. For that, the pole must be here, but I cannot place this over the root locus. Even if I vary k, the root locus will not come here. Will not come here. It will be on the root. Root locus is away from that point. This is the desired pole. Desired pole. I want to keep the pole here, but the original system root locus is not passing through that. If it is passing through that, I can find, suppose the original system is like this. The original system is, my desired pole is here, and here the root locus is passing through. That means, the root locus is passing through. That means, what I have to do is, I have to find the value of k at this point. I have to find the k at that point. That's all. Design is over. But the problem is not like that. The root locus is like this. Root locus is right like this. But desired location of pole is not passing through the root locus. And the root locus is not passing through the desired pole. In that case, I have to bend this. I have to bend this, and it should pass through this desired location of poles. I have to bend like this. If you bend the root locus, then it will pass through that pole, so that I can find the value of k at this point. I can find the value of k at this point. How to bend? For that, this subsystem is included in the original system. How to include the subsystem into the original system, that we'll see now. That is called lead compensation. For that, they can specify damping ratio, undamped natural frequency, or dominant closed loop poles, or overshoot, raise time, settling time. By telling all this, we can find a subsystem so that the root locus will pass through the desired location of poles. Suppose the original system is unstable. By including a subsystem, we can make the system stable. Suppose the original system is unstable. By including a subsystem, we can make by including a subsystem, lead compensator, we can make the system stable. That is also possible. Similarly, when the system stable but doesn't give desired response, as we have seen, it is not passing through the desired location of poles. In that case, we can bend the root locus by using lead compensator, and we can make the root locus pass through the desired location. We can find the value of k at that point. So these are all possible by using lead compensator. How to design a lead compensator? The steps are, for a given performance specification will be given. For that, we have to find the desired location of poles. Desired location of poles. Like this. This is the desired location of poles. What is the given? Zeta and omega n are given. So if this is the length, omega n is given, angle zeta is given. So I can find the desired location of poles. This is the desired location of poles P1 and P2. So I have to bend this root locus to pass through that P1 and P2. How it can be done? By using lead compensator. These are the steps to design the lead compensator. The first step is for a given performance specification, choose the desired dominant closed loop poles. First, choose the desired dominant closed loop poles. Then check whether the root locus of original system is passing through that. My desired location is this. The root locus is passing through that. Then why I have to modify the root locus? No need. I have to find the k value here. That's all. Design is over. If so, find the k at the dominant closed loop pole. That's all. Problem is over. If root locus does not pass through the dominant closed loop pole, root locus is going through this, it is not passing through that. Or the root locus is like this. A root locus is like this. Root locus is like this. It is going this way and it is going this way. But my dominant pole is here. This is the dominant pole. This is the dominant, this is the desired pole. This is the desired pole. So I have to bend this root locus like this. I have to bend the root locus like this. To bend, I can use a lead compensator. That is the fourth point. If root locus does not pass through the dominant pole, dominant closed loop pole, dominant desired closed loop poles, dominant desired closed loop pole, then design a suitable lead compensator to be inserted into the system. Where we are inserting the system, where we are inserting like this, instead of K, earlier we put K only here. Now we are not putting K, we are putting S plus 1 by tau divided by S plus 1 by alpha tau multiplied K. This is we are including here for lead compensator. Like that, you include a suitable lead compensator, find and insert in the system. Then how to find the lead compensator? Find the angle of deficiency, because a point will be on the root locus if it satisfies the angle criterion. So I am selecting one point. In that point, the root locus is not going. If it wants to go through that desired point, means what is the deficiency of angle that we have to find? That is angle deficiency phi we have to find to make the root locus pass through the desired location of. Find the parameters of lead compensator Kc, T and alpha so that it meets the angle deficiency. So subsystem meets the angle deficiency. Subsystem gives that additional angle. Original system angle plus subsystem angle, if you add, it will be odd multiple of 180 degree. So that root locus will be modified. Find the open loop gain of finally find the K at desired location of pole. Check again. If it gives the desired performance, that's all. If it doesn't give, again, step 6 to 8, again and again, you have to modify so that you will get the desired location of poles.